Ferranti Bracknell Computers. Peter was at Ferranti for 32 years, originally assigned military contract work for the Royal Navy. The talk will cover Peter's introduction to programming computers and his contribution to the software for various machines developed largely for Royal Navy real-time ship-borne systems and other computers developed at Ferranti's Digital Systems Division in Bracknell. He's going to discuss the rationale behind the Hermes F1600 range order code and the emphasis on quality control procedures. So, over to you, Peter.
Good afternoon. Can you hear me?
Yes.
No, that's all right. I was motivated to offer a talk on this subject when I heard the one from Jonathan Aylen about Argus computers. Now, there's always this history of rivalry between Bracknell and Cumbrian and Manchester. So I realised that Bracknell was constrained in the same way as, for security reasons, that lots of their work wouldn't be talked about for some time. So that was my motivation. A few words about my introduction to computers. Now, the synopsis of this talk said I was going to give an introduction to programming computers. I'm not. I thought it would be a bit daunting if that was what I was going to do to you lot, but it's my introduction to computers. From 55 to 58, I was at UCL, University College London, doing my PhD in theoretical physics. I had to solve differential equations. I was using Braunschweiger and Facet hand calculators. But after attending a talk by Dr. Buckingham, one of our lecturers, on the department's new tool, it was called a computer, and it was made by Andrew Booth of Birkbeck. I programmed it to do much of the calculations for my PhD, and I was hooked. So having used the machine at UCL, I went job searching for computer work. I did eventually start with Ferranti in June 1958. I was interviewed and initially reported to Stangill, but was assigned to Bracknell where I worked. For the first 2 weeks with the company, I went on a Pegasus programming course in Portland Place before starting off out in the huts in the grounds of Lily Hill that had been under construction when I went down to see them at interview time. Stan sent me on an EdSat2 programming course in Cambridge, not surprisingly I suppose, and I did attend his monthly meetings in Portland Place of his computer research group until I was formally transferred to the Bracknell Digital Systems Department when it was formed and the separation from Ferranti and ICL took place. This background led to my using the words orders instead of instructions and store in place of memory and probably another number of terms which are in current usage, but there we are. I also used the word program with 2 M's and an E in my offering as a joint paper to the Royal Society on my research work. And it would all change to the word program with only one M on the end, no ME. I thought that was very un-British. And I thought, how could the Royal Society of Britain be non-British? But there we are. I've been overtaken by events. My first computer I worked with at Bracknell was called ADAC-N. The ADAC was Action Data Automation Computer. What the M stood for, I don't know. It was connected to another piece of equipment called ADAC-D, which handled analog input from radars and passed digital data to the digital machine. The project was from Admiralty Surface Weapons Establishment at Portsdown. I think they chose that name because they realised that Admiralty Research and Surface equipment wasn't a very good one as an acronym. But never mind. They wanted a means of using computers to assess the feasibility for their use in the Royal Navy, with particular emphasis on interfacing with the prototype 984 3D radar that dominated the skyline over Portsdown Hill for many years. ADAC-M was constructed using panels, each of 2 or 3 logical circuits in NOR logic, using the design by my scribble of Withenshaw. You see, we did talk to each other, so it's a bit of a slander to say we didn't. ADAC-M had 20-bit words, 6 function bits, 2 modifier bits and 12 address bits, a fairly conventional structure in those days. The core store was huge, 4,096 words, with an access time of 12 microseconds, which I think was pretty good for that time. So simple orders took this 12 microseconds. The core store was initially rather too volatile, as the power supply had a waveform that frequently departed from the desired square wave, such that until these problems were sorted out, running programs was a rather frustrating task. The machine had to be frequently bootstrapped using hand keys and reading various things from 5-hole paper tape. On one occasion, during a thunderstorm, it was noted that 3 lightning flashes were required to fill the accumulator with 1, as shown on the display. The software I provided consisted of simple initial orders and some input-output from to and from paper tape, arithmetic, trigonometric subroutines. A standard program sheet was devised, and I was actually involved in commissioning the machine. To aid program development before the machine was delivered to ASWE, I did write a simulation on the Pegasus at ARL Teddington, which is adjacent to the grounds of NPL. I was familiar with this machine, so I've used it over many months to study another problem of tracking jammers, from which a radar could only get direction. If they're coming in up there and they jam you, can only know they're in that direction and not the range. That was an interesting study, but not really pertinent to today's talk. When one of the ASWE programmers came to run on ADAC-M, a program previously proved on my simulator on Pegasus, she was upset to discover that nothing happened on operation of the run key, until I pointed out, but you're looking at the console of the machine, that in fact it had run quite successfully and perhaps rather more quickly than in the simulator. As ADAC-M, as delivered to ASWE, was the only machine of its type. As a result of successful experience with ADAC-M, ASWE decided to get Ferranti to go ahead with the design and manufacture of a computer system for potential use on board RM ships. Now, what problem are we trying to solve? The ship system requirements. Input from sensors, radars, sonar, data links, ship's compass and gyro. I want to know where you are, it's quite useful. Weapon systems, and depending on the type of weapon system, this could mean any of all, or aiming, launch control, or in-flight control of those missiles. And then you've got the command consoles, the weapon system consoles in the control room, and all sorts of switches and lights giving the state of the system in use at the time, whether it's an exercise or not, or all sorts of things. So to fulfill these requirements, they had to be fast for real-time operations. For example, there could be well over 100 aircraft detected in one radar revolution at 12 seconds. The majority of these perhaps could be in one active quadrant. Each of these positional detections, supplemented by another 50 to 100 or so from data links or to ships on shore, needed to be correlated with previous hits to calculate the velocity of the vehicles that they were looking at. and there will be many false echoes, and to discard them without risk of losing a good contact itself took time. All input data was to be used to update a track table. We probably call it a database nowadays, a track table holding a complete battle scenario with details of all the vehicles in the area, including identifying track number, its coordinates, velocity, its type, characteristics, whether it was ours or theirs, if it was ours, it was IFF codes and all sorts of things like that. The many displays in the operations control room had to be continually updated. Some of these would be a mixture of the process data and the raw radar data, and therefore you had this 12-second cycle again that you had to handle. Each vehicle was identified by having a little plaque of characters associated with it, giving some details of its track number and so on. There had to be enough remaining capacity to deal with the peak demands of missile control. In addition, the machine needed to be physically robust to cope with harsh on-board environments and to have at least some non-volatile program store, so that if you did lose all your data for power supply failure temporarily, you could hopefully get back again quite quickly because you didn't have to reload the program. Initial development started at Lily Hill and moved to Western Road in Bracknell in October '63 when DSD was formed. Ashley's experience with ADAC-M suggested that 20 bits was not sufficiently to give sufficient accuracy for the tasks, so we chose 24 bits. That brings us on to Poseidon. Our logical designer was Jeff Nutter. Unfortunate name perhaps, but there we are. His aim was to maximise the performance that could be attained with the technology available at the time, basically a 2 microsecond beat time with 6 microsecond volatile store access time. He came up with a 2-order code system with a conventional outer order code and a free address inner order code. The outer order code was implemented by calling up inner orders held in the first 256 words of main store, effectively microprogramming in more modern parlance. His theory was that to use a long store address field in each order was wasteful, particularly where most store accesses would be in sequence rather than random. The adoption of 3 short addresses and effectively regarding the main store as an indirectly addressed peripheral of the CPU would allow a greater number of function bits per word, leading to more operations being performed in a given number of store words and in time. The computer was initially named Neptune, an appropriately nautical god in the Ferranti tradition. This happened to be a useful acronym for Nutter's easily programmable type for use on naval exercise. However, it turned out that name had been chosen for the atomic reactor on HMS Dreadnought, so we had to change it. So we changed it to the Greek equivalent of Poseidon. Come up with an acronym for that if you like, but I haven't managed it. The outer order code had 13 address bits, 3 modifier bits and 8 function bits, and it's fairly conventional. Not all possible function combinations were assigned, and there were 5 modifier registers. The inner order code had 3 5-bit function fields designated U, V and W. Sorry, 3 3-bit function fields designated U, V and W, and 3 5-bit address fields. You could combine the A, B and C in some orders into a 15-bit address field. In order working, a number of operations could be carried out at the same time. For example, a counter could be incremented or store address advanced. This is the interpretation of the inner orders, the in order addresses. Sorry it's so busy, but there's an awful lot of information there. 0 and 1 are 0 and 1, so you don't really need much logic to implement that. 2 and 3 are the program store contents and the data store contents at the address held in a register which is at the end of the store addresses available. Beta, alpha and mu are fairly common names for the accumulator and related registers for two word working like in multiplication, division and so on. Kappa is another register which is used as a collate register, so that if you set bits in there and you read a store address, you only select those for which it's 1 in this kappa, so you can select bits from the track table to look at quite rapidly. In group 1 orders, this is the intercomputer highway, so you can talk to other machines or other equipment. But for other orders, other groups of orders, it's called Q, which is Q stats, and this includes a number of staticizers which you can use, program some of them. One of them is the overflow stat, for instance, so you can't clear and test that one. That comes as a result of your logic working, but you can test them and so on. And they're useful. These 3 are general purpose registers. This is a full length one of 24 bits. This is the 11 bits, least significant bits of that one. And then 1 to N5 are the 13 more significant bits of the general registers. You can refer to them separately altogether. And these are your general working registers. This is the order number register. This one is which one of these is, depending upon the setting of the modifier bits in the outer order word. 22 is a counter, which you can increment and test as other orders are ticking over. 30 is the link register. When you could do a jump and store the current address in that link register, and then it incremented it, and you could go down this linked nest. So if you hopefully got out of subroutines in the reverse order that you went in, otherwise you got in a bit of a mess. Hardware features. It used germanium transistors. It was very robust to satisfy the military specs I mentioned. The development model was subjected to a drop test in which a running machine was physically dropped, lifted up on chains and dropped a foot or so onto a concrete surface, and it continued to work. There was a publicity film made of this test, but I'm afraid I've been unable to locate a copy. The system is required, as I said, to have fixed non-volatile program store so that you could recover quickly. For program development, a volatile store could be made available either as dedicated program store or as part of the data store. Several types of fixed store were developed. The first one, for the prototype model, had printed circuit boards with a diode connected to one of 7 tracks to give 1 octal digit. So a 24-bit word required 8 diodes, and there were 32 words on a card. Programming that with a soldering iron was not quite as easy as punching a bit of paper tape. But anyway, we managed to do it. This is one of the, a picture of one of the fixed store panels. I do have a number here with me, so that's what it looks like in real life. That's my scanned picture of it. Not very good, but if you want to see it, it's there. This was clamped down by these notches and things between the cores, and depending whether this was connected or not connected, it gave you a 0 or a 1. You could make minor changes to that with a bit of a scrape or a soldering iron, but not advisable. Initial orders was written, I wrote that, supporting both order codes. This gave you program input and output for documentation purposes. Routines were provided to effect intercomputer transfers, which initially required synchronisation between the two machines to make sure that things could go with the right timing across the intercomputer highway. A contract was received from ASWE to supply an autocode for the Poseidon computer to a specification to match that Pegasus autocode. We called this flow pack because it was taking point numbers. The first ship to be fitted with a Poseidon system was HMS Eagle, an aircraft carrier, which was the first one with the 984 radar on it. The system was called ADA, ADA, Action Data Automation, all in capital letters, not to be confused with the A, small d, small a for Ada Augusta Lovelace of later fame. It was designed to collect and process data for the track tables as I've already specified. And this time we were to be involved in some of the early programming work. The Eagle system had 4 equipment bays in the form of a capital H. 3 of these were Poseidon computers. The 4th was for analog to digital conversion of the radar signals for input to one of the Poseidons. The other 2 machines ran the same programs on the same data simultaneously, with a view to providing a fallback if a difference were detected. I never did work out the theory of that myself, because I don't know how you decide which one should continue if they were different. The control console was at the centre of the H and included a hideously complex switching unit above called Proctor. After Eagle, 4 Batch 2 destroyers with 2 Poseidons each were fitted, starting with HMS Fife in June '66. Here's a picture of 2 Poseidons being commissioned at Western Road. I did spend an action-packed week on board Eagle during its trials in 1964 after the refit, which included the installation of the Poseidon system to assist with troubleshooting. I boarded from the dock at Plymouth and left by climbing down a rope ladder to a tender off Portland. In the time between, the ship went up and down in Line Bay with trials of aircraft landing and taking off, increasing away from Sea Vixens to Gannets to Buccaneers. When the latter were fired off the deck, the steam catapult mechanism was stopped rather violently at the end of its run after each aircraft release, causing a shock wave which reverberated several times from one end of the ship to the other, gradually tailing off over a period of 10 or more seconds. I learnt why the computer had to be robust. Development models of Poseidon were sometimes available at Western Road for various in-house projects. One was as an aid to production for the wirelists by taking the connections from the logical design and generating them and putting them out in a sequence of increasing length for the wireman to do in a sensible way. So they added them in layers. And this layering became important when we progressed to multi-layer printing of the backboards, as we did for later production versions of Poseidon, because you had the same similar selection process to get the short ones and then the longer ones in the higher layers. I did also produce a simulator for Hermes, the next generation of machines to run on Poseidon. By the way, the robustness is not really a very modern requirement. There's the Temple of Poseidon in southern Greece, and that's lasted a few thousand years, but that looks rather robust to me. As experience of Poseidon grew, it became clear that the free address order code did enable faster running programs to be written, albeit at the expense of greater need for programmers to be aware of the machine structure. This seemed to confirm Jeff Nutter's theory about the free address effectiveness and coloured our approach to the design of the next computer range, eventually termed Hermes. Hermes had no single address code. It only had the free address code. Early machines employed germanium NOR logic operating at a clock rate of 1 megacycle per second. The concept of range was important. It was essential that logical design could take advantage of future advances in basic technology of components and circuits, but still allow implementation of software-compatible computers with a great spread of computing power. This led to the much more logical order code, again the 25th verse, FIDS ABC, which is down at the bottom there, 3, 1, 2, 3 in the function bits, and again 3 5-bit address bits. With this structure, the function set could be designed with common meanings for bits across the whole code, minimising the amount of decoding logic required, leading to a physically smaller machine for similar power. The parallel adder was designed for speed and to minimise the number of different PCBs required to ease maintenance and reduce the number of spares required. There are 23 user registers styled V1 to V23. V0 was always 0. Which these were in the basic machine, these were in the 6 microsecond core store, but could be replaced by fast registers built in logical elements in batches of either 7 for the first, and 0's always 0, so the first 7, and then 2 lots of 8 after that. You could have as logic registers, which could obviously be accessed in the machine beat time of 2 microseconds. There are 4 store address registers, styled N0 to N3. N0 is the order number counter, the address of the instruction being obeyed, and the others are all data store addresses. And the 29 to 31 are that's the order being obeyed is 28. 29 to 31 is the contents of the store. The address is held in these N registers. The function code is obviously then quite complex, but you've got F, 0, 1, 2 or 3, and the arithmetic is plus, minus, and or not equivalent. And its operations with tests, if I have 0, and I is 1 to 3, you get these same operations, but with store address manipulation, extra counts and things like that built into it. 4, 5, 6 and 7, 0, again it's tests on words or Q stats. Now when you say words, you can test any bit of any word for a clear set, where you can test it and set it. If I is 1 to 3, you get the whole range of the logical shifts, send around carries and all sorts of double length, logical double length arithmetic and so on. In the miscellaneous is the jumps, the absolute jumps, and the jump and store link. The link nest mechanism uses a pointer NL, and if you store something in it, it increments it by 1. And you can also store working registers in the link nest as well. So if you're going to a subroutine and you have some conventions about how registers are used, you want to use those that have a special purpose, you store them, and then you can get them out before you leave the subroutine. All of which all leading to what Harry Johnson coined the phrase, a function-rich order code, to make it sound very good, which is what it was. To facilitate programming in this order code and insulate programmers from some of the numbers, we introduced fixpack, so named to distinguish it from flowpack, because most of the interpretations of orders in our programs would be as fixed point numbers. It used the same telebit symbols as flowpack, but we've progressed to 8-hole tape now. Here's a couple of examples of orders you could write. You jump to somewhere labelled 1, V4 plus V5 is greater than or equal to 0. The jump address is either VA, and would be the next one, or is relative, because if you can have, if A is treated as a signed integer, which you can have by use of D equals 1 in the order, you could jump 16, minus 16 or plus 15 places from here where you are, and it would be in one word rather than taking up the extra word. The actual choice of function bits to implement that a fixpack instruction would be sorted out by the so-called fixpack compiler. What did Hermes look like? Well, there's a picture of one. I think that might be the one that we sold to NPL Teddington in 1964 under commissioning in Bracknell, but I'm not sure. Power supply at the bottom, core store there, logic up there, little display panel there, console here, tape reader, tape punch, useful table to stand it all on, and an engineer. This is where it gets personal. That's not Peter Niblett, that's Peter Redman. Some of you people from ICL may have known him. He worked at Lily Hill, and he was for some time a commissioning engineer on Perseus and did go out to Sweden with it. I was his best man when he married a tracer from the Lily Hill drawing office, and he was my best man when I married one of my programmers, so that's the end of the personal bit, but there we are. Our successful experience with their early ship-borne systems led to the need for smaller and faster computers to try to satisfy their intention to add more information to their wide range of ships. They supported our move from the simpler Hermes structure, and the exact compatibility of order code was an essential feature. The F1600 range was then started, reducing the basic machine to 3 shells rather than a rack full. An expansion capability was a must, and if any extra facilities were added, floating point was mooted at some stage, it came in a few years later, you still had to have software backwards compatibility. Nomenclature. For some reason, we didn't choose a Ferranti god this time. We had the letter F, which was imaginative or unimaginative, wherever you look at it. And the numbers after it were the number of blocks of core store, the 4K blocks, the speed of that store in microseconds, the number of fast registers. So the basic machine had 1 block of 4 store, no fast registers, and it was 6 microseconds fast store. We did sell some systems, such as an F2207, which is 7 fast registers and 2 microsecond store and 8,000 words. But the names apparently caused confusion in the minds of some of our potential customers who suspected that we were trying to palm them off with a new untried design. So we gave up. And from now on it's an F1600 with all these variations in it, and we have to use all those long words. Some relatively small systems using F1600, I believe, were supplied with programmer support for Wembury, weapon testing, Aberporth, West Wales, and Woomera, and to HSA Hengelo, which is a subsidiary of Phillips, who were developing a radar for the Dutch Navy, which our Royal Navy were considering for some time. With the prospect of further RN orders, we developed the FM 1600, the first machine in the range using integrated circuits. This basic machine only required 2 shelves. This was soon followed by the FM 1600B, which only required 1 shelf. In the early 70s, the RN identified the requirement for a new range of ship-borne computer systems called CASE, which stood for Computer Assisted Action Information System. It aimed to provide assistance to operators rather than trying to effectively replace them with over-ambitious automated systems. The expectation was that with a more limited specification, a physically smaller and cheaper system could be produced, which would be cost-effective, fit on a wide range of smaller ships. We entered a commercial fight with Hermes over this, and they were proposing a system based on their 900 series machines, I think. We won that fight based on our proposal to use our FM 1600B, supported by STEP, our standard equipment practice, which meant that we had modules of the sort of construction that could be slotted together into the robust cabinets, etc., etc. They were all compatible with the FM 1600B itself. Common interfaces catering for a variety of operational input-output equipment, such as radars, sonars, weapon systems, displays, etc. Our existing team of experienced operational programming staff. Systems could be assembled from available units and program components to match varying requirements. We effectively cornered the ship surface ship market. To support their operational systems use, the RN needed to train their personnel to use the new facilities effectively. This led to a series of contracts for trainer systems installed in the Cook building of HMS Triad in the grounds of Southwick Park, just north of Portsdown. There are 2 streams in this work: one to provide replicas of each type of ship system for training ops rooms crews, including Ankara Leander, Type 21, 22 and 23 frigates and Type 42 destroyers. For the trainer ship systems, the operational programs were used where meaningful with minimum modification. This allowed the trainers to be kept up to date by rapidly adopting the latest versions of ship software. The second stream of work there was termed the Combined Tactical Trainer, with its own software designed to create realistic environments in which those ship systems could operate, either singly or in groups, by simulating geographical situations, enemy and friendly vehicles and so on. CTT went through 4 stages over the years. It included the ASTT, the Action Speed Tactical Trainer, to train command officers. There's the ASTT, or a picture of it in up there. As a number of you know, this facility closed only recently, July last year. I believe its longevity is a tribute to the hardware and software design and implementation of the teams based in Bracknell. To cater for this increasing work, Teams of programmers were established not only at Western Road, but at ASWE and HMS Triad. We also won contracts for RN submarine systems, necessitating another team at AUWE Portland. Our sales staff gained us contracts for the Brazilian and Argentinian navies, as well as some cooperation with the Dutch Navy. And we had systems at their research station at Leoc, and I already mentioned HSA Hengelo. To support all of these contracts, as well as people working on the operational program design, specification and implementation, we needed specialist programmers who could work with the engineers to provide driver programs to control transfers between the computers and the various interface units, to assist in commissioning new equipment assemblies such as each ship outfit, initially on our premises and then on board ship, providing test programs for customer acceptance of the equipment, and maintenance programs to help with fault finding and repair by suitably trained RN ratings, often in hostile environments. I don't mean necessarily in action, but not very pleasant environments, as perhaps most computer systems in the commercial field were largely pampered, I think, being air conditioned always. Usually it was only necessary to identify a system fault down to printed circuit board level, as repair was by placing the faulty card or spare. The faulty card could be repaired offline and then returned to the spare port. The main program writing language was fixed-back, one-to-one correspondence generally between fixed-back instructions and orders written and actually obeyed by the machine. The assembly part of the compiler arranged for the incorporation of subroutines from a standard library, providing mathematical input-output, etc. programs, or from project-specific libraries. Listings and other documentation aids could be output. As we had flow diagrams for FlowPack from our Poseidon contract, we could easily produce a FlowPack compiler for Hermes F1600. I certainly use this for generating a number of programs for my own use to assist me in managing the increasing numbers of programmers and projects with which I was concerned. We were asked by ASWE to consider the provision of a compiler for COL, Computer Online Real-Time Application Language, the definition of which had initially come out of RSRE Malvern for the programming needs of a particular army project run by Mr. Gibbs. As we eventually gave us a contract for a COL compiler, as we felt that at that time we did not have the expertise or manpower available for that task, we subcontracted it to a new software house called CAP. A number of early meetings were attended by Alex Dagapayev and Barney Gibbons in person, and later on Lawford Russell was involved. I remember Barney turning up at a progress meeting with a box of washing powder called Coral. Most of the implementation was by a chap, I've forgotten his name, but he'd worked on the STC Jovial compiler, and that was useful experience. This compiler was not used much, if at all, for operational program generation, as at that time the capabilities of the hardware could not overcome the inefficiencies of the compiler for real-time applications. A couple of years later, a so-called more elegant version of Coral was produced by the research arm of RSRE by Curry and Griffiths, which came to be known as Coral 66. So we had to call our version Coral 64 to identify it. By then we had more suitably experienced staff. We produced our own improved compilers for both Coral 64 and Coral 66. They had much in common, particularly in the code generation phase, although the parsing phase was different as the language differed slightly. We also produced a Fortran 4 compiler, which a number of our customers used. When Ada came along, this is a small d, small a, we realised that we were unlikely to be able to compete with the software houses such as SDL, so did not attempt to generate a compiler ourselves. However, we did need to keep up with developments in view of Ada's potential use for our own projects. We were involved in discussions to form a consortium, which we called Augusta, to work on the development support environment for Ada programming, but these came to naught. We did, however, contribute significantly to Ada UK, with our Garth Glynn as chairman for many years and WJ Bill Taylor as a major contributor as technical expert on language features as Ada progressed through its various updates. Although Ada was promoted as a mod standard, it really wasn't really adopted for our end systems for one reason or another. As our teams grew, it became increasingly necessary or essential for the methods and standards by which programs were designed, written, tested and assembled into program suites to be comprehensively documented, with the major task of managers being to ensure that these procedures are followed. Our generation of our own in-house procedures facilitated the reuse of program modules and preempted the MOD requirements to demonstrably adhere to written procedures. We had some very interesting discussions with mod quality control inspectors who had no previous awareness of programming. With increasing programming work, it also became necessary to have dedicated in-house software development facilities at each major site. What had been acceptable just in the early days to use a prototype machine or model under commissioning for program development obviously became quite impracticable. We set up in-house facilities based around Hermes and F1600 grade machines, looked after and run by dedicated computer operators on a 24 hours a day basis. We employed other support staff, styled programmers assistants, to assist with program tape preparation and program documentation, including flowcharts to our designated standards, adequate program listings, etc., relieving the more qualified and experienced programmers of what they considered to be mundane tasks. We ensured that these PAs, often with perhaps GCSE maths at most, had an optional career path by a supported study towards HMC and then to programming roles. Several progressed very successfully in this way. The following slides list documents supporting the languages and procedures just described. These were made available to all programming staff by having a set in each office. After I left Ferranti, I kept my set in our loft at home for many years until pressurised into a clear out. I donated mine to the Museum of Science and Industry in Manchester, where it joined the Ferranti collection. Introduction to programming. There's two supervisors for operational programs, a big one, a mini one. Public library subroutines came in 2 volumes. There was a test system which enabled you to run programs in a simulation type mode before you tried to run it on a target machine. And we did have a magnetic tape user manual, mainly because we had these magnetic tapes on our in-house facilities. Very few, if any, of our customer provided systems had magnetic tape associated with them. We had Coral 64 and 66 manuals and Fortran manual. And then we went on to quality control procedures. These came through various generations, some of our own and then some following developments outside. So we had these available and we tried to follow them wherever we could. To keep pace with the customers' demands, we need to recruit good staff, some with previous programming experience, but many as new graduates. In those days, there were no computer science degrees, so we selected people with a mix of maths, physics, or related backgrounds. There are certainly very few with programming in any language, let alone in fixed back. We participated effectively in the university milk round. My introduction to this was an illustration of the Ferranti way. I was asked by Tom Lunt, company personal manager, to meet him at the University Arms Hotel in Cambridge in time for dinner one evening. Very enjoyable. After breakfast the following morning, I was expecting to be able to observe the master at work interviewing potential graduates. However, as he entered one room, he pointed me into the next room and saying, "Here's your list." And so I was a bit in at the deep end. I got through the shock, and at least one of the candidates I saw that morning did join us and became one of my senior staff. We also took on ex-RN officers familiar with the ops room environment, who were invaluable in specifying the operational rules which would lead on to programme specifications. The number of new people we were taking on required a series of company and department induction and training sessions, often in early autumn to suit the dates when new graduates wanted to become available. Training in fixed pack and our own types of systems was initially done by myself and my experienced staff, but then passed over to the technical publications and training department. And they produced formal manuals and courses for both in-house use and for customer students. At some stage in the mid-70s, I had 500 or so people reporting to me. I'll now go on to illustrate the extent of our involvement with the Royal Navy. I'll go through these quite quickly, but if you do want any further discussion, I'm quite happy to come back to them. Starting with the Sinon Eagle, which I've mentioned, and then the 4 counter-class destroyers with Poseidons. We then go on to Nash's holding the Type K82 destroyer, HMS Bristol. That was the first one with FM 1600s on board. And it was a test bed effectively for modern technology and weapon systems, which were incorporated in many subsequent ships. She had several new features, including missiles and so on, and the advanced software, our computer system. The aircraft carrier CVA-01 was intended to have another FM 1600 based system on board, but it was cancelled, and this cancellation led to there being no more Type 82 destroyers because they were designed to escort the aircraft carrier. Next came the Sheffield class destroyers, Type 42. These had GWS 30 missiles, XSX, and a brand of software called Angles 4. 2 vessels of this type, with some different weapon systems, were sold to the Argentinian Navy. Note that 2 of ours were lost in the Falklands, but not as a result of the actions of their vessels, which kept out of the way. After that came the case ships, including the Type 21. 2 of those were lost in the Falklands. The under-class frigates, Type 22 class frigates, all different editions. And then, I'm sure you'll be pleased to hear, other ship systems, of which I have got very few details. The total number was about, we had on about 80 ships, but these are 3 invincible carriers, the Hermes carrier, 9 counter-measure vessels, and 7 plus submarines. I think there's about 10 altogether. As well as a number in the so-called stone frigates, which is their name for shore establishments. Other Bracknell computers. Our main contract certainly accounted for most of the sales of the F1600 series, but we did have other machines and customers. Apollo was developed in the huts at Lily Hill at the same time as Poseidon, with similar circuits. Was installed at Oceanic Air Traffic Control Centre at Prestwick in 1962, where it remained in operation until at least 1983. It was programmed by us, one chap, to generate flight progress strips used by air traffic controllers to monitor traffic across the Atlantic. They had these little strips which contained the identification of the flight and its last position and where it was going, and they moved these up and down on boards. And so the Apollo was initially providing the bits of paper which stuck on these progress strips. But it started off in that sort of experimental use, so as confidence in its performance and reliability increased, it did become effectively part of an online system. It had 24-bit word, 14-bit addresses, 7 function bits, 2 modifier bits and a spare. The order code was fairly conventional, but with some functions particularly useful for handling alphanumeric characters. Here's Apollo at Prestwick in 1971, with a very youthful looking Herbie Gray, who was the project leader. The Apollo team had subsequent success. I mean, they built up this experience of air traffic control applications. And they had success with ATC operational systems and with simulators used to train ATC controllers based on F-1600 series machines, with installations in Herne, down near Bournemouth, in Holland, in Denmark, Australia and Taiwan. We also had another one called Cerberus. It was designed to help control data links in an army application. It was installed in mobile cabins. I have very little information on this because it was effectively most of the work had been done before I became even aware of it. Another machine which we were involved with was the F100L, which was an early 8-bit single-chip microprocessor with 16-bit addressing, developed by cooperation between Ferranti Semiconductor Department and Bracknell Logical Design Engineers about 1977. It was really very early on in the arrival of microprocessors, and in true Ferranti tradition we didn't really get on with it. We produced extensive software to support it to run on an F100L development system or on a hosted DEC VAX system. Well, I hope that's given you some idea of the sorts of things that we did down in Bracknell. Novel 3 address order kits, code and the support software, mainly RN but other things. And with that I will come to an end and ask if you've got any questions. I do have a few documents and bits and pieces which you may be interested in, which I've got over on the table there, but over here.
Thank you very much. Questions?
Can I just give you the microphone? One.
Sorry, I'm Ellis Thomas. I did work in Bracknell and Cumberland at one time. The end of the line on 1600 series was, of course, the introduction of the military Argus, which, of course, was from the rivals in Wythenshawe. But there was a 1600 D&E. Were they ever used in any systems?
Oh yes, they were used. They didn't come under the term of early ones, which is why I left them out. But they're later ones which were compatible software-wise, and they were used in some of the. I think there was some in the trainer systems at the Southwark, and on some of the later ship systems as well. The military Argus was another development, sort of coerced by the ministry to bring these different arms together, and that was quite an interesting exercise in itself. Again, I didn't think that came under term of early.
Hello, Sheridan Williams. I started life working for the Royal Armament Research Development Establishment at Fort Housted, which was where the Britain's atomic bomb was developed. But when I started there, I joined the computer department simulating the flight of missiles. And my memory of the computers there, first one was called Amos, was a Ferranti, because I saw a label on it. But of course, in those days, when you're only about 17 or 18, you don't recall these things. And the next computer that I think they developed also was a Ferranti called Cosmos. Now, I put that time in with, apparently they were modified, highly modified, that used for wargaming.
I'm not aware of those as being products of Bracknell.
No.
They may have been derivatives of the Argus from Withenshaw.
Yeah. I need to do a bit more research, I think, on that one.
Yes, I'm not aware of those.
Okay, thanks.
What's he like
Sir. I'll just fit in when you said Withenshaw.
Oh, what's wrong with Withenshaw?
No, sorry, no, I'm getting some of the Argus.
My name's Chris Smith. I worked for a number of years for Hawker City Aviation and later British Aerospace. And we had an Argus, not an Argus, a Hermes. You said earlier on that when you weren't aware of any customer machines when they going to take.
Well, I'm unable to find much information on where they went to, but that's an interesting one.
Did you have enough store to keep compilers in memory along with the programs, or did it have to come out on paper tape as an intermediate stage? And if you did, were there any attempts to speed that process up with external magnetic devices of any kind?
There was no compiler. You only had compiled programs in the operational system. You compiled them offline and then you generated the one that went in. So there was no compiler in the operational system. I don't know if that answers.
I was thinking rather more that the process of software development
the process of software
was
development
quite slow if one had
well, that's why I said our computer centres did have magnetic tape for that sort of purpose, and that was probably one of its main, if not the only purpose for which it was there. It was fraught with difficulties at times, but it did work in the end.
Ryan Richmond, who's never had anything to do with Ferranti. I'm curious to know, with your early machine, your Poseidon machine, you said it had a 6 microsecond store, and it had to look after what seemed like an awful lot of equipment in 12 seconds.
Yes.
So, did you succeed in meeting those goals?
It did. Yes, it worked. I mean, it worked on HMS Eagle for several years, quite successfully. It was a job to get everything in. You didn't have much stock. The track table took up a lot of room, and it took a lot of time driving the displays, as well as processing the radar input. So it was a bit of a struggle, which is why I think we needed to get down to a very close to the machine language or code to be able to get the advantage out of it. You could program the loops which were done most frequently and most often in a precise and concise way using the various parallel processing capabilities of the order code.
But didn't your programming methods imply that you had to fix the number of aircraft that were in the sky or something, which might have caused difficulties?
No, you had to deal with the number that were there, and I just gave an example of the numbers there might be. You're talking about aircraft, it might be 1 to 100 or more, which you were actually interested in and could want to track because they were part of your battle scenario. So yes, it was a challenge, but I think by the way we approached it and the code and the conciseness in which you could write programs and how you could optimise loops when you went about it by identifying the bits that were done most often, you could tune it to maximise the benefit of the technology then available.
Sounds very impressive to me, thank you.
This is a loaded question.
Sorry?
This is a loaded question.
No, it's not loaded, no.
You used to work for me.
Yeah, I used to work at Bracknell, not Nigel Benning. I was told a story when I was there that I loved, and I repeated it to other people in good faith. but it was to do with an old machine, and you might be able to validate it or not. The first drum storage that was fitted to a submarine was fitted with the axis vertically. Horizontally, and it was discovered that when the submarines went around corners, it sheared the bearings off. Is there any? That's what I've told people.
I haven't heard that one.
It's one of your engineers told me.
Yes, I haven't heard that one.
They just remounted it vertically. And it was
from the same place, I prefer to remain anonymous, but I do have a technical question for you, Peter, which is, can you identify the attractive brunette with white high-heeled shoes on one of your earlier slides?
No. I don't think it was Joan. I don't think so. My recollection of her as being a little bit plumper than that.
Another round, we went to Australia. Should we go back and look?
You might even want to see that one. Keep going backwards. No, that's before that.
Very good picture.
That one.
That was one, yeah.
Who was that then? You telling me?
I thought that was Anne, but I might be wrong.
It might be Anne. Yeah.
Do you know the year of that picture?
Well, it must have been 63 or 64 because it's at Western Road. You can tell by the floor. They didn't have floors like that in Lily Hill. Or parking like that above it. And, on the time scale it must have been that because they started deliveries on whether these were two for Hermes, for Eagle, HMS Eagle, I don't know. Could well be. You didn't ask about this? It's too far away, isn't it?
Just to take the story on, you mentioned Dryad closing down last summer. Yes, HMS Dryad closed down last summer, and I can confirm that several van loads of that equipment were taken to various places. Some went to the museum in Swindon, some went to the museum in Haverhill, and I believe they got some of the kit going. Quite a lot of the kit went to the Museum of Computing at Bletchley Park, including some impressive equipment called a coastline generator. We're looking for volunteers to come and get this working for us. Would you be interested? Secondly, on a purely personal point,
I went to part of the ASTT, wasn't it?
It's a device that shines light or perhaps an image of known targets through a photographic plate with the coastline marked on it, which moves around in XY axes to simulate the radar image back into the ships.
Yeah. It's quite an interesting piece.
Quite an interesting piece of kit. On a purely personal note, I went to interview in Western Road, Ferranti Bracknell in 1966 for a job interview. I'm still waiting for the answer. Could I have it, please?
I'm George Felton. I come from a very different background, although it was strong. I was a commercial, and other influence was very few types of machine, but many of each type. And this created quite a different atmosphere because you had many types of machine and only one or two of each.
Yes, it is a bit different. Yes. They're compatible, hopefully is the word.
Well, Peter, thank you very much indeed for coming to London and giving us such an interesting talk and the interesting pictures and the artefacts you brought on programming Ferranti computers. So thank you very much indeed. Thank you all for coming, and our next presentation is going to be on Thursday the 21st of February when Keith Van Rysberger is going to talk about a history of information retrieval. So I look forward to seeing you then. Thank you.